So setting that aside, let's compare DuckDB to Pandas and SQLite as well as Postgres for analytical tasks, where DuckDB clearly is going to have some advantage over the other tools. Because one of the big differences between SQLite and DuckDB is DuckDB stores its data in columnar fashion in order to facilitate fast columnar analysis, exactly what a tool like Pandas does. And because it can perform these analyses on files, not just in a memory, if the data set we're looking at is too large to fit into memory, well, we can't even compare against Pandas at all. Pandas isn't even a starter, but DuckDB may still be an appropriate tool to use, if not another database product. Well, here I'm going to take the original 36 million row data set, and I'm going to perform some simple operations. I'll read this in to just see how long it takes for me to read this in from Pickle, which would be a fairly fast reading process, at least fast in reading it in from CSV and performing a bunch of conversions. I'll do a single series, single column mean in Pandas. I'll do the same thing in SQLite. I'll do the same thing in DuckDB, and I'll do the same thing in Postgres. And there's one or two small details that make these benchmarks a little bit hard for us to really pin down. I'm trying to avoid allocating too much memory, so I'm going to loop over each result one at a time as opposed to allocating the entirety of the return data set all at once, just to make sure that I don't run out of memory on this particular virtual machine, but also to make these examples somewhat equivalent. In the case of Postgres, that will be slower than if I do some kind of batching, and it'll be the same case for probably SQLite and DuckDB, but unfortunately DuckDB doesn't provide us with the ability to fetch these rows in some kind of batched fashion. And so we're going to have to look at these rows one at a time, and we may get some unnecessary slowness or some artificial slowness just from the cost of reading in each one of these rows and constituting a Python object for each of those one at a time. But whatever the case may be, let's actually take a look at the timings here. It takes us about 1.5 seconds to actually read in the data. It takes about 0.05 of a second to do a simple single column mean on this data frame. SQLite is very, very slow at doing the same mean on that one column. It takes 11 seconds in total. It's a very large file as well, so you can imagine some of that may just be reading the file. DuckDB, however, is quite fast. It's about within an order of magnitude of the speed of what we might assume to be probably the simplest possible operation we could do in Pandas or NumPy, a mean of a single linear data set. And you can see that DuckDB is even faster than the Postgres services that's running on our machine. In general, we'll see that DuckDB is going to be faster than SQLite by a significant margin and competitive, if not typically faster than Postgres, despite being a little bit less general than Postgres and a little bit less fully featured than Postgres. And in some cases, we may even see that DuckDB approaches the speed of Pandas itself. Let's take a look at another simple benchmark. Here in this benchmark, I want to do something that's a little bit more complicated. So instead of doing just a column-wise mean, I'm going to do a grouped mean. The result here should be one mean per category value. And you can remember that the original data set had relatively low cardinality. I think there was about 1,000 different categories for 36 million rows. So these are fairly large groups that we're looking at. And of course, we'd have to redo these benchmarks in the case of high cardinality, many different groups, to see what the difference would be. Although in the case of Pandas, we can imagine that probably the speed difference won't be very significant. We'll perform this test in Pandas, in SQLite, in DuckDB, and in Postgres. And we can take a look at our timings. Reading in the data, again, is about 1.5 seconds or so. Do note that this data is being read in from a local drive to this particular virtual machine. In previous examples, I was actually writing this data out to a shared drive using QEMU virtio-fs, which added enough overhead to all of this to skew the benchmarks a little bit. But this should be a fair benchmark. If we look at the group by mean, it's actually relatively slow, even though, do note, in order to speed up this group by, we pre-sorted the data on that one level of the index that we're doing the grouping on. So whether or not we want to count this 1.4 seconds and the 6.7 seconds in the 2.5 seconds that Pandas takes is really up to what you think. Is it the case that you often have data sets where you load them once and do a bunch of things on them? In this case, I think maybe you don't really count this or you amortize this cost. Is it the case that your data sets are typically pre-sorted along the facets of the data set that you're typically doing group bys on? For me, that's a very common thing, and so I might not count this in that many circumstances. I don't really end up doing that many additional sorts, and I'm often doing group bys on data that has already been sorted in the way in which I'm going to do those group bys. We can see SQLite again is very, very slow, but DuckDB really pulls ahead here. DuckDB is blazingly fast at this, even faster than our in-memory data set, even if we don't include the reading of the data and the sorting of the data. And in fact, you can see that Postgres is somewhere in the middle between these tools. Obviously, it's going to be the case that even materializing the return value for this is going to be relatively expensive for Postgres, bringing that back over the network, but you would expect Postgres to be pretty good. It's still somewhere between SQLite and DuckDB. Now, let's try one final benchmark and a slightly more complex example. And for this example, I wanted to choose a problem which I knew would be difficult in pandas to see, is it the case that even if the out-of-memory benefits of DuckDB don't help me, maybe it allows me to, through its API, do tasks that are hard to do in pandas or hard to express in pandas, cases where I might otherwise do something like drop down to NumPy. And so for this example, we'll do our classical grouped weighted summary statistics problem. We're going to look at each group, and within that group, we're going to look at the value and the weight column, and we're going to compute the weighted mean. And for those of you who are very familiar with pandas, you know that if we were to try this with a .apply operation on the group by in pandas, it would be excruciatingly slow. .apply on group by in pandas is the only way for us to look at two columns at the same time. So it's the only one expression way for us to compute a grouped weighted summary statistic, but it is extremely slow. So here we'll skip that entirely and we'll look at the .ag decomposition of this problem, where we compute this as two .ags and we do a division. And we're even going to give pandas a little bit of a benefit by avoiding one spurious index alignment here. We could even try to avoid one index alignment here, although that shouldn't be necessary since pandas should be able to avoid that index alignment for the timing. We'll do the same thing in DuckDB and in Postgres, and we'll skip it in SQLite just because we just don't expect SQLite to be a competitor here. Again, reading in this data is relatively fast in this case. And let's just double check that we read in the data. Yeah. So a little bit faster for us to read in the data. Why that is not clear. There could be some caching issues here, but we're going to compare more or less these data sets, or at least these results, to each other. And a surprising result that we can see is even the fastest version that we can do in naive pandas is still an order of magnitude slower than the naive version we can execute with SQL, where, let's do this one here, where we're just doing a sum of the values times the weight divided by the values and the weights. Now, if we uncomment our third example, let's rerun that one more time just to take a look at the results. But if we comment our last example is dropping down to raw NumPy, which we've experienced previously when we've looked at this problem, about another 10 times speed up. So a question would be, can DuckDB exceed the speed of doing this at the raw NumPy layer, eliminating some of the clumsiness and some of the limitations of pandas? And if we rerun this, we'll discover that there's definitely some FS caching that's happening that may skew these results very slightly, but we'll discover that DuckDB is quite a competitor here for these kind of grouped weighted summary statistics or other simple statistical analyses. In fact, I would say that there may be cases where you may discover that taking your data that's in pandas and dropping it down to DuckDB may in some cases be faster than the equivalent that you can do in pandas, just as a consequence of fundamental limitations of the pandas API. For example, that group by operations cannot look at two columns at the same time if they're, say, a group by ag or group by transform. Now, I want to talk about how we conceptualize this kind of speed. Because when we talk about tools like pandas, we often talk about the idea of the strategic computation domain. Namely, that we have a Python program that has all the generality of Python. That is to say, it is capable of expressing any computation that we can write in any form. And we have this restricted domain where we have certain restrictions. In the Pandas API, there are certain things that we cannot express fluently. For example, we can't express group-weighted summary statistics very easily, or any sort of group by that looks at two columns at the same time. We can't express any operations that need to store some state as they perform operations down the rows of the data frame. So for example, the amount of interest and the balance that I have to pay in that classic home ec high school example of here's my home mortgage and I'm paying $100 a month and the interest rate is 5% and this is how much I owe. Things like that can't be expressed easily in the Pandas API either. They couldn't be expressed very easily in Python, but at the cost of being very slow. And so we have this idea of a restricted computation domain, a restricted portion of our program where, subject to certain restrictions, as long as we stay within that domain, things are relatively fast. And there are restrictions not only, for example, in terms of the underlying data types that we can represent, where a Python integer has the ability to automatically promote, so there's no minimum value, no maximum value, no overflow, no underflow. When it comes to something like a NumPy ND arrays in64, well, it's just a regular machine-typed in64 with all of the issues that may come up if you exceed the maximum or are lower than the minimum.